Section 16.4 is on page 1000. Talks about Green's theorem in the plane. Recall, this is from the last section, actually 16.2. If f is conservative, if you remember what that meant del crossed with f is the zero vector, then we could find this function f such that if you apply the gradient, and remember the gradient function is the partial with respect to x, the partial with respect to y, and the partial with respect to z. The gradient applied on this f will give me the vector field, where the vector field is m, n, and p. Right? And remember, we were able to find the integral of f dot dr to be f of b minus f of a in that case. Remember, this was the integral of f dot t dot ds, and we called that work. So we did that over and over. We also called it circulation. I'm just recalling all of those for you. I'm going to do that in every section until we get the hang of this. Now, two things that they define here. I really don't care much about this definition here. I care about one component of it. So the k component of the curl, I care about the curl. The curl of f is del crossed with f. We already know that. And the divergence of f is del dotted with f. So this is the partial with respect to x, the partial with respect to y, the partial with respect to z of, and f is normally m and p if it's 3 dimensions. Here it's going to be the partial with respect to x, the partial with respect to y, and the partial with respect to z dotted with m, n, and p. So this is a vector. This is a scalar. But I'll entertain, again, I really don't care much about this k component. It doesn't really mean much because we're going to use a totally different approach to this, but no big deal. Let's find it. So the k component of the curl of f. Curl of f is del crossed with f. And if you remember in the previous section, that was flux dotted with the k component. I, j, the k component, right? And if I'm dealing with a 2 dimensions, if I take the curl of f dotted with the k component, right? That would be partial with respect to x, partial with respect to y, right? And 0 for k, and this would be m, n, and 0, and that would be what? So the I component is 0, the j component is 0. It turns out the only piece that will remain would be the partial of n with respect to x minus the partial of m with respect to y. And if I dot that with 0, 0, 1, which is the k, I wrote it, 0, 0, 1, which is the k component, that would be 0 plus 0 plus, guess what? Right there. And the reason I'm deriving this, because that's how we're going to do things. We're not going to really memorize these formulas. We're going to understand how this works, and we're going to really circulate around those two definitions. And that's pretty much it. So from the previous section, we dealt with flux, and we dealt with circulation. This was circulation. And flux was del crossed with f. Do you remember that? Section 16.2. Well, now let's elaborate. Let's do a couple of examples on this first. And again, I'm just doing this for practice because we're going to be doing this a lot. Find the curl of f. The curl of f, by definition, what do we see up there? It's really the curl of f, the k component, I'm sorry, of the curl of f. It's the curl of f dotted with k. Actually, it turns out to be just that if you're talking about 2 dimensions. So either you do all of this work that I did right there already for you, or you say, you know what? Well, the k component is going to be just the curl of f dotted with the k. And again, this is 0, 0, 1. And instead of doing that, you could say that is del crossed with f. And that is the partial with respect to x, the partial with respect to y. And wouldn't that be the m? And that would be the n. And that would be simply the partial with respect to, that's a 0 minus the partial with respect to y, that would be x squared, which is simply negative x squared. And that works out identically. I messed up a bit. Just a bit. That was a minus. So when you take the partial, I thought that's what multiplied. This is really x squared minus y. So the partial with respect to y is a negative one. So that turns out to be a positive one. Now in the next problem, I could do it the long way, just show you it turned out to be the same thing, just to get that out of the way and convince ourselves that this always works. So if I take the curl of f dotted with k, what they want us to do, they want us to say, well, look, that is the ijk, right? And that is going to be the partial with respect to x, the partial with respect to y, the partial with respect to z, and it's going to be x squared y, xy squared, right? And 0. And if I take the I component, so that is the curl of f. That is del crossed with f. That would be, if I look for the I component, that would be 0 minus 0. Not that it matters, and I'll tell you why. Negative, the j component, that's going to be 0 minus 0. And the k component would be y squared minus x squared. Now, do you see that no matter how I do this, I'm going to dot this with just the k component? Doesn't that mean the only piece that's going to remain is actually y squared minus x squared? So why go through all of that pain? Or I could simply say, if it's 2 dimensions, it's simply del crossed with f, and that's it, right? And that would be what? That would be the partial with respect to x, the partial with respect to y, and x squared y, xy squared, and that would be the partial with respect to x is y squared minus the partial with respect to y would be x squared. And there it is. No need to go through all of that pain. And now the core of this section, Green's theorem, there are 2 of them. One for circulation, one for flux. We did those already. We did circulation, we did flux, except we did it the long way. And let's figure out what this is saying. Let C be a piecewise, smooth, simple. I mentioned that that's going to happen all the time. Here's the key. Closed. Closed. If it happened to be closed curve enclosing a region R in the plane, let F be a vector field with continuous for partial derivative, all of that good stuff, you know. Then the counterclockwise is positive rotation. The counterclockwise circulation of F is equal to, well, let's see. Let's start from the left. This we did already. That was in 16.2. This, in case you're not seeing it, that is mn dotted with dx dy. So if you're not seeing that, that's f dot dr. which is in 16.2 as well. We did that already. Look what it says. It says instead of doing that, what you did in 16.2, all of that work, guess what? You could find the double integral. This right here, so it's saying it's equal to the double integral of curl of f dotted with k. If it's two-dimension, if you're talking about two-dimension, then guess what? The curl of this f dotted with this k vector, right? That is actually nothing more than del crossed with our f. We just showed that on the previous examples. That's the only reason I showed those. So guess what this integral is? This integral is the double integral over region D, which is the area. We just had a test over this of del crossed with f. And there it is. Isn't that amazing? Awesome, right? dA. Cool? So I have another way of finding circulation with one catch. I need this to be closed, and they're going to give us problems in which we're going to go ahead and do this using 16.2 the long way and using this shortcut. You're not going to see it until you see an example. And then we did flux, and they have another one for flux. They say let C be a piecewise smooth simple. The same condition again. It has to be closed for Green's theorem to apply. Over a region with the same idea. Now this was, and if you remember, we did that back when we did flux, and we said the outward flux, we said this was, remember, this is mn, right? And oh, I'm sorry, this is, we said, if you remember, that was del crossed with f, right? No, that's not what we said. This is f crossed with dr. That's what I meant to say. Yeah, f crossed with dr. We did that in 16.2 as well. If you look at the notes, you could see it. And it says, instead of doing what you did, guess what? This is the double integral of, and look, this is del dotted with f dA. Alright? And this is for the flux. So now we have one for circulation and one for disbursement. And that's pretty much it. So we have two equations. Equation 3 deals with circulation. We're used to doing f dot dr. Now they're saying, well, guess what? Just take the double integral of del crossed with f dA. That's do the trick. That's circulation now. And the flux we had back then was, that shouldn't be there. The flux we said, that's f crossed with dr. Those are both in 16.2. They're saying now instead of doing that, you could do del dotted with f, the area of the region, and guess what? That's it. Now I want to try number 8 and do both of those, and let's see how that plays. It says verify that Green's theorem, right? On equation 3 and 4, take the domain of each. We did something like that on number 30 and on 12. 16.2, I mean, not 12, 16.2. So that's a circle. And we want all of that. This is the diameter of A. Let's see how this works. There's R. And T varies between 0 and 2 pi. So, if I want to find, like expression 3, if I want to find the closed integral of C of f dot T ds, that would be the integral of f dot dr. That is the integral from 0 to 2 pi of A, the sine of A, the cosine of t. Oh, I'm running out of time. Okay, you know what? I'll start this in the next section. So in the next video.